So welcome again. In this session, we are going to study the properties of vector addition and scalar multiplication in the plane. So, theorem. So, properties of vector addition and scalar multiplication in the plane. So this is what you want to what you want to give. So first, know that any vector in the plane is of the form V is given by V1, V2. So we say, and remember, so these are the notation that this is the notation that we are going to use. So we'll represent vectors as V, and then you put an arrow on top, or we can write it V, put a dash at the bottom, or we are going to write V and then tilde sign. So all these will be the notations for vectors. And then when you write V1, V2, these are elements of the vector V. So let's leave the properties. So properties. One, actually before we go to one, let's just give the general definition. So let U and V be any two vectors. Let U, V, and W let U, V, and W be any three vectors in the plane, and let C and D be any two scalars or real numbers. Let so let this one be the usual addition and scalar multiplication respectively. Then, so we have, so remember, because we're saying that this u, v, and w are vectors in the plane, then u can be written as u1, u2, v is v1, v2, and w is w1, w2. So 1, if I pick u and then I add to v, I find another vector, just the sum of those two vectors will be another vector in the plane. So it's a vector in the plane. So such a property is called the closure property for addition. So this is closure property for addition. You see, this is what you're trying to say, that if I pick u, which is given by u1 plus u1 comma u2, so u is u1, u2. When I add to v, which is v1, v2, then I get, remember, I get the sum of corresponding elements, so it will be u1 plus u2, and then comma u1 comma u1 plus v1. So u1 plus v1 comma u2 plus v2, which is just a vector in the plane, because all the vectors in the plane are of the form x comma y. So this is the x value, this is the y value. And then number 2, u plus v plus w is the same as u plus v plus w. So such property is called associativity. Associative property for addition. For addition. So this to say, so u is given by u1 comma u2 plus v is v1 comma v2, and then w is w1 comma w2. So this will be the same as saying u1 u2 plus, now here I'll have v1 plus w1 comma v2 plus w2, which is the same as saying u1 plus v1 plus w1, and then u2 plus V2 plus W2. And because U1, V1, W1, W2, and V1, V2, all of them are real numbers, then we can also associate and write this as U1 plus W1 plus V1, then plus W1, and then U2 plus V2, W2. And you see this the same as saying U plus V and then plus W. This is the interpretation of what we have there. I remember we started from saying U plus V plus W. So you see this and these are the same. Another property, this is V1. Number 3, U plus V is equals to V plus U. So this is commutative property for addition. Commutative property for addition. So this is the same as saying U1, U2 plus V1, V2 is the same as saying U1 plus V1, comma, U2 plus V2. Add corresponding elements, which is the same thing as saying V1 plus U1, because these are just real numbers, and then V2 plus U2. And you see, this is the result obtained by saying vector V plus vector U. So therefore, U plus V is equals to V plus U. So this commutation. Number 4, if I have U plus a 0 vector, then I get just U. So this property is called additive. This is additive inverse. Additive identity, not inverse. Additive identity property. So 0 vector is what we call the additive identity. So these two, just for illustration, U is U1, U2, and then 0 vector in this respect is 0, 0. So when I say U1, U2 plus 0, 0, then these are just real numbers. So you'll have U1 plus 0, and then U2 plus 0. These are real numbers, so any real number plus 0, you get just that real number, and then this is just U2. which is just the same as the original U vector. So therefore, U plus 0 vector just gives us U. Number 5, then there exists an element. So U plus negative of U gives us a 0 vector. So this is called additive inverse property. So for illustration, you pick your U, which is U1, U2. When you say negative U, you are negating every element. So you have negative U1, negative U2. This will give you U1 plus negative U, and then U2 plus negative U2. So remember, these are real numbers. So U1 plus minus U1 is just 0. U2 plus minus U2 is 0. And this is the 0 vector we're talking about. So therefore, U obeys that property. Number 6, C times U is a vector in the plane. So this is also called closure, but then now with respect to multiplication. So this is closure property for scalar multiplication. E.g., if you say C and then U is U1, U2 will be C U1 and then C U2. You see the result is still the same structure for all vectors in the plane. It's one number, then another number. So that's why I'm saying that CU is just another vector in the plane. Number 6. That's number 7. If you have C, then you multiply by U plus V, then you get CU plus CV. This is what we call distributive property. So you have C and then U1, U2 plus V1, V2. So this is the same as C into, so U1 plus V1 and then U2 plus V2. So this is the sum of these two vectors, U and V. And so this you can write it as CU1 plus, actually I can just write C times the sum of the two. So I have C into U1 plus V1, comma C into U2 plus V2. So which will be CU1 plus CV1, comma CU2 plus CV2. That's what we have. So U2 and this result is not different from saying U, so U plus V so C times U plus C times V. And so C into U plus V is given by CU plus CV. So that's the distributive property. Actually, to see it clearly, you can say this is the same as C into U and then plus C into V. Because actually this is the sum of these two, then simplifies to this. Number 8, if you have C plus D, multiplied by U, then you'll have CU plus D du. Are they still distributive property? And then number 9, if you take C du the same as C D, and then you multiply by U. So this is associative property. And lastly, if you take 1 multiplied by U, then you still just get U. So 1 is called multiplicative identity. Multiplicative identity. So multiplicative identity 1 is what gives us that result. So before we stop, that's what we call vectors in Rn. So a vector in n space is represented by an ordered n tuple. For instance, an ordered pair forms x1, x2. So this is called R2. And then ordered triple forms vectors of the form x1, x2, x3 called R3. So this is called sometimes 2 space, and this is called 3 space. And then ordered quadruple forms, so vectors of this form, x1, x2 up to x4, x1, x2, x3 up to x4. This is called R4. So this is sometimes called 4 space. And then the same process continues up to ordered n tuple forms, so x1 up to xn. This called Rn. So this is n space. So remember, this one is read as R4. This one is read as R4. This one is read as Rn. Then this one is read as R3. This one is read as R2, or 2 space, 3 space, 4 space up to the end end space. So any vector in 2 space that is R2 is of the form. So these are key points of the form x. You can write it as x1, x2, or you can represent it as x equals to, you put in column form x1 and then x2, or you can write that vector as, just write x1 and then some space x2. So those are the different notations we'll be using. And then second point, any vector in 3 space that is R3 is of the form so we write x, you just write x1, comma x2, comma x3, or you can write x equals to x1, x2, x3. So this is the column form, or you write it as just x1, x2, x3. So all these notations will be used interchangeably to mean the same. Similarly, any vector in 4 space that is R4 is of the form x equals to x1, comma x2, comma x3, comma x4, or we can write it in column form. X equals to x1, x2, x3, x4, or you can write it as x equals to x1, x2, x3, x4. And in the same manner, any vector in n space, that is Rn, is of the form x equals to x1, x2, x3, up to xn. Or if you don't want to use this, this representation, you can write in column form as x1, x2, x3, up to xn, or you write in row form x1, x2, x3, up to xn. So all these different forms given here will be used interchangeably to mean the same thing. So finally, let's define a vector addition and scalar multiplication for Rn space. So definition so let U be given by U1, U2, U3 up to UN, and let's have vector V, V1, V2, V3 up to Vn be vectors in Rn. Let's see be any scalar, that's real number, then the sum of vector U and vector V is defined as the vector. So when you add these two vectors, or they have the same size, so it would be U plus V, you simply add corresponding components. So you have U1 plus V1, U2 plus V2, U3 plus V3, up to UN plus Vn. So this is the sum of those two vectors. Simply add corresponding components, and the scalar product, or the scalar multiple of U by C is defined as a vector So U times C, or C times U, is given by, you take this C, you multiply by every component of U. So we have C U1, C U2, C U3, up to C UN. So those are the two definitions for vector addition of vectors in Rn and scalar multiplication of a vector in Rn. So next time we'll define what to mean by a space and then what to mean by a vector space. So this is vector addition. And then this one is scalar multiplication. In Rn. So this is also vector addition in Rn. Thank you.